Okay, perfect. Good afternoon. Thank you for being here in physical presence. I appreciate it very much. Any question, curiosity with respect to the previous lectures? Okay, and don't hesitate if you have any question. First of all, a communication. I had to change, make a minor change, one change in the calendar of the lectures. Just 1 second, it's here, because I cannot teach on April 22nd. So we need to make a break now. And today is April 8, as you know. Next time will be April 29, and then the final lecture on May 6. It's here. The next two lectures will be same room, same time, Monday, 2:30, 5:30. I apologize, but I have to attend a conference abroad to talk about climate change, as usual, and therefore I cannot be here. Any question related to this? Okay, perfect. I still have to put on Alma Exami the exam dates. I will do that. In any case, I will open the subscriptions beginning of May for the exams before summer. I also will publish later on the date for September. There will be another date in September. As you know, the exam dates are those three: June 10, June 27, July 15. And I will give you details, more details on the exams later on, because I will tell you where is the location, and depending on the number of students who are subscribed to each exam date, I will tell you the timing, how we will get organized. Meanwhile, if you have any questions, just let me know. Okay, now let me go to the point where we got last time. We discussed during the last lecture, we discussed the history of Earth climate in general, and we started from the biggest, from the big scale, from the big picture, and then we zoomed into the more recent times. And in particular, we were discussing, when we closed the last lecture, we were discussing the progress of temperature during the past 2,000 years. It seems to be a long time span, but of course, as we discussed, you know that compared to the geological time scale, it's nothing. And indeed, if you think about the number of generations from 2,000 years ago to today, they are many, but not hundreds of generations. You know, any generation is supposed to last 25 years. So in order to cover 2,000 years, we have less than 100 generations. So even if you think at the human time scale is not that long. And nevertheless, during this period, which is, as I said, like a few seconds with respect to the geological time scale, we had several climatic variations. And here you can see the reconstruction, one reconstruction of the global temperature based on isotopic content of selected cores. And you can see that in particular, we had two warm periods. One that is called the Roman warm period that lasted during the Roman Empire, as we discussed. And in particular, it ended, the temperature went down basically at the same time when the Western Roman Empire collapsed. And there are interpretations, of course, historical interpretations that attribute one of the causes of the collapse of the Roman Empire to this change of climate, because it is demonstrated that during warm periods in many parts of the globe, the conditions are more favorable to prosperity. Of course, during warm periods, you have some parts of the planet that become inhabitable. But overall, in the Northern Hemisphere, for most of the Northern Hemisphere, we can say that indeed the historical historical records show that prosperity periods were coincident, were occurring at the same time than what are called the climatic optimums. And then, there was about 300 years of, note the length of these cycles, few hundreds of years. There are other cycles that are longer, but these cycles we are talking about now, they are not very long. There was a period that was about 400 years, from like 500 to more or less 900. That was cool, was quite cool. And then we had the medieval warm period lasting from about 900 to something around 1300s. And this has been also a period of flourishing conditions in Europe, as we know. If you look at the history, it was the period where the municipalities increased their prosperities. And then we had the onset of the Little Ice Age that ended around 1750. And the picture of Venice, it's what I mentioned while closing the last lecture, the picture of Venice with people skating over the lagoon. And it means that, the lagoon is salted, of course. It means that the temperature was really something that was importantly cool. So what are the reasons for these changes? This is the big question. We explored so far these changes occurring on several time scales. But the big question, the big research question that is still open is what are the reasons? And researchers dedicated a lot of efforts to study climate change since we discovered the ice ages, and it is about 200 years ago. And since then, researchers dedicated a lot of efforts trying to understand what is the reason, what could be the motivation. And as you may know, because this is also part of our culture, and there are several initiatives by the media to inform the public about past changes, the possible reasons. I mean, the media cover climate a lot, and even before the onset of global warming, because climate is something that has a general interest. And therefore, as I said, there were several researches and some important discoveries, which I would like to discuss with you now. And first, we know that the climate system is complex. It's a complex system. It's a dynamical system. It's dynamical system means that it's a system that is fueled by external forcing, by several forcings, and there are several interactions between some subsystems that we identified and we isolated because we think they are extremely important. So there are tight connections between the atmosphere, which is often considered as a subsystem of the climate system, with its own science, atmospheric sciences. Interaction with vegetation through ecosystems, in particular, ecology is the science. Land surface, and interaction with the land surface means that there is a strong interaction between the atmosphere and the land, the morphology of the land. So there are orographic effects on precipitation, there are changes of temperature varying with the altitude, and then there is an interaction with the ocean system and with the ice system. Oceans are particularly important because they occupy a lot of surface over the globe, and they are able to store a lot of heat and a lot of carbon. So indeed, they play a relevant role. Ocean circulation is an important element of the climate system. And to describe this connection is not easy. We know this because we already discussed the reliability of the available climate models. And describing these systems is complicated in itself, and then the connection. So it is a complicated system, and this is why we cannot really understand what causes the changes. And it is a system that is also dominated to some extent by chaotic components. So what are the theories that have been the possible explanation for climate changes that have been developed so far? So here you can see three possible explanations: changes in plate tectonics, changes in Earth's orbit, and changes in sun's strength. Now, let's try to discuss them one by one. First of all, let me mention briefly the changes in plate tectonics. You know that the land, the surface of the land is moving according to theories that are in the domain of solid Earth and which explain the evolution of the geography of the land. This evolution comes at the expense of several movements of masses around the globe. And the movement of these masses may provoke changes in the inclination of the Earth's axis, for instance, changes in the behaviors of the Earth orbit. And moreover, there is to say that, the dynamics of the overall climate is influenced by, as I just said, ocean circulation of vapor, which is influenced in turn by evaporation, and also exchange of energy, heat from the land and the atmosphere. So if you change the displacement of the lands and therefore the displacement of the ocean, indeed, you can understand that there are perturbation of these systems, perturbation of evapotranspiration, perturbation of air movements. You understand that if you displace the continents in a different way, climate changes, and also the global temperature may change. These are first possible explanations. And then I'm not talking much here on changes in sun's strength, but indeed the sun is the fuel of the Earth system. It's the propeller. As we will see, the Earth system is a closed system. I think we discussed this already. So I can say, as we discussed, it's a closed system, meaning that there is no exchange of matter, no flow of matters between the Earth system and the surrounding. There is only one exception: it's energy, incoming energy from the sun. So this means that the energy that we find over the Earth, we will discuss energy later on, starting today. The energy is energy coming from the sun in different forms. For instance, perhaps stored in fossil fuels. Fossil fuels are accumulators of energy that the Earth received from the sun in earlier times. So the moral of the story is that if there is a change in the strength of the energy flux from the sun to the Earth, there is also a change in climate, a corresponding change in climate. And we know that sun's strength is changing continuously. Of course, the big question is these changes confined within the limit of variability, which means that It means that, I mean, they are up and downs, but no permanent changes. This would mean that climate, the big changes in climate that we had were not caused by changes in the sun's strength. Or another possibility is that indeed there might be some at least long-term shift in the sun strength. And so that, for instance, the current global warming could be caused by a change in incoming energy. This is a possibility that is not very popular, is not very credited in the scientific community, because the scientific community is mainly convinced to a very large extent that global warming is caused by the greenhouse effect. So it is not very accepted that global warming may be related to other explanations, but it is, we don't have the final answer to that. And by the way, keep into account that the sun is not eternal. So it is eternal for the time span of our life, and more than that, it is very slowly varying during geological times. But we know for sure that this energy that comes from the sun will come to an end in the very far future, we suppose. So, I mean, the fact that there are changes in sun strength is something that is physically plausible, physically accepted. The question is whether these changes are responsible for the current increase of temperature, of course. And the dominant theory tends to reject this possibility. But let's look into more details. What could be the causes related to changes in Earth orbit? And let me mention Milutin Milankovic. He was an astrophysicist and a mathematician, and he worked in the last century, in the 20th century, and made very important discoveries during the Second World War. And basically, he explained the long-term paleoclimatic change, glacials versus interglacial periods, by proposing a theory that relates these changes to changes in the geometry of the orbits of Earth and Sun. And basically changes in eccentricity, obliquity, and precession of the Earth-Sun system. Let's look in more details. What in particular are these changes? So first of all, one cause of climate change could be a change in its eccentricity. You see in the left figure, the sun in orange, the Earth in blue, and the red circle, which is not a circle, by the way, it's an elliptic orbit of the Earth around the sun. And eccentricity is expressed with the analytical function that you see below the left figure. And in particular, it's expressed depending on the two parameters A and P. So depending on the position, on the relative position of the Earth of the sun in the Earth orbit, we may have small changes of A and P, but these small changes may have an important effect on climate. Second possibility, obliquity of the Earth axis. axis of rotation. Now you see what is the current inclination of the Earth's axis. It's not fixed. There are periodically some minor changes. And I want to tell you a story which is not demonstrated. This it's a supposition. It's an hypothesis that is not demonstrated. And to tell you the truth, I don't think it is credible. Some years ago, there were global reactions to against the realization of big dams in the East, in Asia. If you look at the list of dams, of the largest dams global list, it's on Wikipedia. If you look at the global list of largest dams, I think maybe that we already had a look together, I'm not sure. But if you look at this list, you will see that the most recent ones are in Asia. The reason is that they started later. In the Western world, dam construction started earlier, and therefore we have exhausted our opportunities for large dams. In Asia, they are indeed continuing realizing very huge dams, and thanks to the improvement of the technology and also thanks to their favorable conditions, they were able recently, you may have heard of the Three Gorges Dam in China, they were able to build very huge dams. And you know that water is heavy, and therefore some scientists postulated that this concentration of mass of water in huge mass of water in a point location, in several point location, may have changed a little bit the obliquity of the Earth's axis. I don't think, as I said, I don't think this is a credible interpretation. I don't think so, because, I mean, if you look at the mass of the Earth, the global mass, and you consider the mass of the water into these dams, it's very tiny. If you consider the mass of the mountains, I mean, I don't think really. But this is to explain to you that when you move masses over the globe, the inclination, the obliquity of the Earth's axis may change. And this movement of masses occurs continuously in the nucleus of the Earth. And therefore, if there is an anomaly in the movement, in the fluid movement in the nucleus, it may happen that the Earth's axis changes its inclination. And keep in mind that we don't know these processes, these phenomena. We don't know in detail what's happening inside the Earth. And there is another possibility, another possible cause of changes in obliquity. And the other possible cause is the impact with asteroids, with meteorites. And we suppose that in the past, you know, one of the possible explanation of the extinctions of dinosaurs was precisely the impact with an asteroid that may have changed the climate. And these impacts are very frequent, as I discussed already with you, because you know, of course, in the time span of the human history, we didn't experience many of them. But actually, in the geological time span, as I mentioned to you already, if you look at the surface of Mars, which is not eroded, it's not modeled by atmospheric processes, it's like a Gruviera. There are a lot of craters. Another possibility, another feature that is relevant in the Earth's orbit is the precession. The precession is, you know, the Earth is rotating around the axis, but it's also rotating around a secondary axis of precession. It's, let me just, in order to better explain, I open a Wikipedia page because I can't find the right English word in this precise time. So let me open, okay, here you see the movement of the Earth in an animated figure. And you see that the Earth axis is in itself rotating around another axis, the axis of precession. And so if you have a change in the inclination of the if you have a change in the precession, this is also another possibility for changes in climate. For sure, it can change seasonality, but not only seasonality, also global temperature may change when you have these features, these orbits that are a little bit modified. And this is clearly understandable if you consider that the whole energy fueling the Earth system is coming from the sun. And it depends on the way the Earth is exposed to this flux of energy. Of course, these are interesting things. There is to say that it is unlikely, as you clearly understand, that these changes may have occurred in the past 30 years in a relevant way. I mean, while these changes may explain an ice age that lasted for millions of years, I mean, to explain what happened, what is happening under global warming with these changes in orbit, it's probably not the more appropriate interpretation. It may happen indeed that in these 30 years, the strength of the sun activity has changed a little bit. And it is not easy for us to measure the sun activity. At least, let's say that the uncertainty in the measurement is such that we cannot explain with these measurements an increase of 1 degree of global temperature. So we can make measurements, but this measurement doesn't have the precision that is required to describe a change of 1 degree in global temperature. So indeed, the strength of the climate, of the solar activity may be an explanation for global warming. Global warming means past 30 years. But if you, the behaviors of the orbits, probably it's not likely that they are a possible, credible explanation. Okay, let me see one thing. Milankovitch also identified the so-called Milankovitch cycles. They are not mentioned here. And let me see in Wikipedia, Milankovitch cycles. Okay, here we are. And you see that Milankovitch cycles describe the collective effect of changes in the Earth's movement on its climate over thousands of years. And in particular, Milankovitch identified an 11-year cycle, which is recognized today has indeed a determinant of climate, but it's not a reliable, credible, and appropriate explanation of global warming. And I think here everything is explained. Okay, so let's move forward and let's here instead there is the analysis of the other possible determinant of global warming, which is the greenhouse effect. And indeed, you already have seen these graphs. The concentration of CO2 in the atmosphere has increased a lot starting from 1950, or let's say it has increased a lot after the Industrial Revolution, with a sharp increase after 1950. And this has been caused by the Great Acceleration, and which is mentioned here. I'm sorry that you can't see the title of the slide, but it is precisely the Great Acceleration. And this is indeed the most credited explanation for global warming. Keep in mind that CO2 is not the only one greenhouse gas in the atmosphere. There is also the influence of methane, which is emitted by the oceans. It's an important greenhouse gas. Another greenhouse gas that is extremely relevant is water vapor. But of course, water vapor, we don't have any information that may bring us to state that global warming became with an increase of concentration of water vapor. And water vapor may increase for increasing temperature of the atmosphere. So probably if there is an effect of water vapor is a feedback that is, I mean, increased temperature means increased evaporation and means probably a higher content of vapor in the atmosphere, but it's not likely to be the cause of it. However, I'm mentioning these greenhouse gases to make you aware that the problem is indeed a challenging one. So trying to understand the motivations for changes in the climate system, whatever they are, is indeed something that is challenging. And I think, okay, let me also mention another thing. I wanted to see the next slide because I want to make sure that there was not a slide on what I'm saying. I want to mention another thing. Climate has a memory, and this memory means that once that you get a perturbation of the system, this perturbation is going to last for some time. It's typical for environmental processes. And if you think of temperature, when you get a cold day, usually it takes some days in order to recover the temperature after a perturbation. And so it is indeed clear that also in the long term, climatic variables may exhibit some memory. While the memory is perfectly understandable for short durations, or for instance, for the time span of days or weeks, or even months for some perturbation, you can understand that it may take some time. For instance, if you look at the river flow for huge rivers, over the Po River, when you get a very low flow, it takes some time in order to recover. Even if it rains a lot, it doesn't recover immediately. It takes some time. So on the one hand, we are aware of this memory, and it is something that is accepted. What it is not unanimously accepted is that this memory may last for a very long time. And like 100 of years, like you get a perturbation of whatever nature, and then it takes 100 of years in order the system to gain back to the previous state. This is not unanimously accepted. And it is this question, this research question, it is the motivation of several controversies. You understand why? Because, I mean, if we accept this idea, it means that the current in 2024 may be influenced by a perturbation that occurred in 1750, 300 years ago. So we have to look for the causes of the current climate, not only in the current situation, but also in the past. It is something that, on the one hand, it is reasonable if you think of it, because it is reasonable that the Earth system may have some very slow dynamics. On the other hand, you understand that it makes the interpretation of what's going on even more challenging. So it is something that is not, it is the reason of controversy. On the other hand, we have some evidences, like, for instance, if we look at the very long record of the annual flows of the Nile River that the Egyptians, the ancient Egyptians took, they went on for 600 years, every year, to make a sign at the max level of the Nile River. You know why? Because they were dependent on that. And they took this sign on the Nilometer. It's an interesting story. If you look at the Wikipedia Nilometer. This is the Nilometer. You see, it's like a staff. They allowed the water from the Nile River to come up in this kind of a vertical tower. So the vertical tower was connected to the Nile River. So for the principle of the communicating pipes, the water from the Nile River went up along this tower. And this is the way the water level in some cases is still measured today. And then every year, of course, the water left a sign of the max. So every year they went down the stair and put a sign over the max and then cleaned it up in order to keep it clean for the next year. And they went on for 600 years. So this is an enormous source of information because we don't have direct measurements of river flow for any river that are so long, 600 years long. We have some measurements for the Po River, but the length is still one of the longest time series of river flow globally. It's Po River is 217 years now, today, 2 years ago. So now we are at 219, okay? 600 is 3 times that. So by looking at this record of the Egyptians, we can see that there are cycles that lasted, cycles of low flow or high flow that lasted for several decades, which we cannot explain. Something that, a perturbation that lasts for like 50 years, it's something that we cannot explain physically. We don't know what could be the reason of that. Of course, you may say, maybe they made a mistake, you know, maybe the person was a little bit too drunk during these 50 years. It was one person that was addicted to drinking a lot of wine and made mistakes. Yes, but it is a possibility. Indeed, the measurement errors are a possible reason of long-term cycles, but we have several other records that justify the acceptance of this idea that there might be long-term cycles. And for instance, if you look again on Wikipedia, this is another interesting story if you want to see it. On Wikipedia, you look for Earth and Earth exponent. Okay. The Earth exponent, if you see here, this is not for your exam, it's just for information, is used as a measure of long-term memory of time series. It relates to the autocorrelation. Autocorrelation is memory, okay? And basically, Ernst was an engineer who designed, projected several dams, huge dams, along the course of the Nile River between 1940 and 1950. I think, I'm not sure if there is a picture here. So let's see if there is a related Wikipedia page. It seems not. Anyway, Harold Earst. I misspelled it. I'm sorry. Sorry, I was looking at the chronology. Harold Earst. Here is the Wikipedia page. Was a British hydrologist who was busy in designing this. His work in Egypt started in 1906 and lasted 62 years. During his best work after he reached 65. So, I mean, it's never too late. And so what he found is extremely interesting. There is a link in my website that with a link to a short presentation of what he found. He was studying the river flow of the Nile River to identify the optimal capacity of a dam. And what is the purpose of a dam? The purpose of a dam is to make a not constant inflow to make it in a constant outflow. So the inflow is variable, is not constant. The purpose of the dam is to make the outflow constant. And you understand that you need storage to do that. You need storage because you have to accumulate flow when it is in excess in order to release it when it is below average. And the storage, you understand, that is proportional to the up and downs. The more up and downs that you have, and the more the storage, the more the variability, the more the storage, because you have to compensate something that is highly variable. But in order to be rigorous, I should say, the longer the ups and the longer the downs and the higher the storage. Because if the up and downs are just alternating very quickly, you don't need a huge storage. But you need a huge storage if the up is lasting for 6 months, like on the Nile River. The Nile River has only one peak. And therefore, the excess of water is lasting for 6 months. And then the deficit of water is lasting for 6 months. So you need, if the cycle is longer, you need an higher storage. And statistically, you have an idea on how to compute it. And Ernst used a statistical approach, and then he used the numbers. And he always found in the numbers a higher storage, and he couldn't explain why. And he studied a lot, he made research on explaining why the storage in the Nile River is higher than one would expect from statistical theory. And the reason is that the statistical theory doesn't consider very long cycles. The statistical theory doesn't assume that, the classical statistical theory. So he made a great discovery that there is something in nature that is related to these long-term cycles. It's very nice. And several scientists later on tried to build their career on understanding why, understanding the reason. And so far, we still don't have a satisfactory explanation after almost 100 years of research, thousands of papers, but we still don't have a satisfactory explanation why these long-term cycles happen. This is extremely fascinating, I think, because anytime that we don't understand something, we should be fascinated rather than depressed. Okay? And of course, we would like to live in a world, ideally, most of the people would like to live in a world that is predictable, because they feel reassured. But actually, I think that if nature was predictable, it wouldn't be here, because anything that can be predicted easily doesn't survive to evolution. The species that survive to evolution, the systems that survive to evolution are systems that usually are unpredictable. And you can find several examples. And the most trivial one is when people are threatened, the first recommendation they get from the authorities is make yourself unpredictable. Don't use the same schedule every day. You have to change every day your habit. This is the most trivial example that I can make. And for animals, and therefore for nature, it's the same thing. Animals are unpredictable in nature. They don't take the same route every day because they know that if they take the same route, the predator will easily get them. And the same applies to natural systems. They are unpredictable. And I think this is fascinating. Of course, unpredictable doesn't mean that we can understand some basic patterns. We can. But one thing is to understand the pattern. One other thing is to make a rigorous prediction. So I'm not really surprised that climate cannot be easily predicted, because I think this is an inherent feature of climate, unpredictability. But still, we can understand the patterns. Okay, this is the final conclusion of my lecture on the history of Earth climate. And be careful. The fact that the climate has always been changing shouldn't be used as an argument to say that we don't have to be concerned by any change in climate that it happens. Of course, one thing is something that is beyond our control. Another thing is something that is within our control. So there are some evolutions, some dynamics that are unavoidable. We can't do anything to avoid them. Think of the impact with an asteroid. It can cause the extinction of the human species, but we can't do anything to avoid it if it is going to happen. So there is no reason to be really concerned. It is something that we have to accept, like any risk that occurs every day in our life. But if a risk can be avoided, we should avoid it. So if I drive drunk, okay, it's forbidden, but besides being forbidden, I know that it's dangerous, it's a risk, and it's something that is under my control. So this is why it's forbidden that I drive drunk. And, basically you take the same risk driving drunk than driving during an earthquake, more or less. But on the other hand, an earthquake is not under your control. So the moral of the story is, climate is changing for sure. We need to know this. We need to take this into account because, if we want to limit the impact of climate changes, we also have to understand the natural variability, not reject it. What I don't understand in some current interpretation of science is to neglect natural variability. Why should we neglect it? If we neglect it, we will never be able to understand what is future climate. On the other hand, the fact that the climate is naturally varying shouldn't decrease the concern related to the human-induced climate change. So I don't think there is anything wrong in discussing with you the glaciations and in saying that the changes during glaciations were much higher than the changes in temperature during global warming. Of course, glaciation lasted millions of years. Global warming is 30 years. So there is nothing wrong in taking into account that natural variability was capable of doing much more than what we are concerned of now. On the other hand, this shouldn't justify that we don't care about pollution, we don't care about environment, we don't care about anything because, okay, so let me close this Wikipedia page and let me go back here. The slides are closing with a consideration which is related to the potential drowning of the Italian coastal plains, so Italian coasts, Italian coastal areas, if some scenarios for sea level rise by 2100 become true. Okay, if this scenario comes true, you see that there are several parts, and especially some sensitive parts like the Venice Lagoon, the Gulf of Oristano, the Gulf of Cagliari. There are basically, sorry because I can't see clearly over the screen, the sea level is expected to raise up to the green line. So it is indeed a quite significant change affecting Venice. So aqua alta, high water would become the norm. On the other hand, there is uncertainty in these predictions. And the conclusion of this slide is, the geological record is the unique tangible record. So it means that when you extend to the future what happened in the past, you are not sure that this is an extrapolation. You are not sure that even if we base our prediction on a careful analysis of what happened in the past, we are not sure that the future under different conditions will replicate with the same pattern that we eventually observed into the past. And this is a crucial point. It's a crucial point because even if we make our best, we have to always consider that the projection into the future is not a geological record. And the geological record is unique. It's only one realization. It's the only realization that we know. And when we project it into the future, I mean, there is uncertainty, and which we discussed many times. Okay, and Winston Churchill said, the further backward you can look and the farther backward you can look, the farther forward you are likely to see. So indeed, it's important that we look at the past, but we have to also be aware that there is nevertheless uncertainty related in any prediction. Okay, I think we can pass to the next one, which is energy. Questions? No questions. Okay, let me close this. And let's look at the next slide, climate and energy. First, let me say one thing. We could make an entire course of 48 hours of frontal lectures on climate and energy, and it wouldn't be enough because it is really something challenging, important, because climate change is CO2 emissions, as you already know, are strictly related to energy production. On the other hand, I think in 2-3 hours, we can get a picture. We can get a picture of the situation and the challenges. It is another controversial topic, unfortunately. So try to distill any information that you get. Try to get an objective interpretation. Unfortunately, there is a lot of ideology related to energy production, related to also to climate change. And ideology means that sometimes we tend to follow a mainstream interpretation, which is based on consensus. Consensus is important in politics, is of course important, because democracy is based on consensus. And so sometimes we tend to follow mainstream interpretation based that gain a large consensus, but it's, you know, sometimes these mainstream interpretations are not derived with a consideration of, with a proper consideration of the big picture. Why? Because the big picture is indeed complicated. An example that I could make is in the past century, when I was a teenager, there were a lot of discussions on environmental pollution, environmental degradation, acid rains, and also a lot of discussions, because it was a period of like today, I mean, not more than today, but it was a period where the young generations tried to gain an understanding and an opinion with respect to geopolitical structure that the global world was assuming, which was by several young teenagers not appreciated very much. It was the period of the Cold War, etc. And there was a long discussion on the opportunity or not to increase the military equipments. And there was in particular a long debate on the opportunity for Europe to build up an army and build a reserve of nuclear weapons. And then there was a strong movement that protested against that and worked for pacification, for peace. And as a consequence, Europe, basically in all of Europe, we decreased the army, the military service was abolished in most of the countries. And Europe, in terms of power of its army, Europe doesn't have a common army, as you know, but even at the national level, with the exception of France, that is the only state in Europe that has nuclear weapons, basically there was a decrease of the armaments and of the military power. And this was a consequence of a movement that worked for that. And I remember that I was really in favor of it. And I am wondering increasingly, after the development that we saw in the past 5 years, if this was the right choice. I'm not sure. This is a personal reflection. But on the other hand, I'm getting more and more convinced that probably also if you look at nature, to reach the peace, probably you also need some strength, some power. And so this is a demonstration of a general rethinking of what could be the right strategy to reach peace. And a similar debate was concentrating on energy. We had a referendum on the nuclear power in Italy, and the referendum, of course, won. So we don't have any nuclear plant in Italy. And then we take the energy from abroad. Now, I was really convinced of the opportunity to give up with the nuclear power production. You know, there were also a couple of incidents. And today I am rethinking also this convincement, because I don't see personally, maybe that I'm not really a very expert on energy production, but I anticipate what could be one of my conclusions. I don't see a possibility to gain, to reach carbon neutrality by 2050 without increasing the nuclear power production. I think it is unlikely that with renewable only, we can get to carbon neutrality. Anyway, this means I wanted to make this introduction, which is take it as a personal reflection, and you may find different opinions also among scientists, not only from the media, but also among scientists, you may find different opinions on that. But I want to make this introduction to clarify that the problem is controversial, and it's controversial for a good reason, because it is indeed a challenging question, a challenging research question for which we still don't have the means to gain a final answer. So let's focus on climate and energy then, and in particular on energy and climate, rather than climate and energy. I take the PowerPoint, 1 second. Okay, now, what is energy? This is an interesting question, and indeed, I want to take this quote from Vincenzo Balzani, and he's an Italian chemist, by the way. He's emeritus at the University of Bologna. He worked just close by here, and he still works, by the way. I think he's 86, 87. And he is a recognized international expert on energy. And the quote, I'm reading it, says, if you want to abash in a way to put under difficult someone, ask him what is energy. Everybody thinks of knowing it. If I ask you what is energy, you have your personal answer and you understand what it means. However, nobody usually gives a clear definition. Or let's say nobody gives the definition that is accepted for energy. Sometimes gives a psychological definition, like energy is what I need to make every day of mine exciting. Sometimes gives a definition based on temperature. Sometimes we get different definitions. So what is energy? Energy is mandatory for every process, as Balzani said, and it appears in different forms. This makes the definition difficult. The word derives from the Greek, and the Greeks, however, intended energy in a philosophical context, as a philosophical concept. So how can we define it? In physics, let's take the definition from physics. Is the quantitative property that must be transferred to a body or a physical system to perform work on the body or to heat it. To perform work or to heat it. There is a fundamental difference, as we will see, between performing work on a body and heating the body. Performing work is equivalent to energy, and work is given by the product of a forcing times a movement. So in order to shift a body, if the body is not moving originally, if the body is in steady state not moving, I need to apply a forcing, and the value of the forcing times the movement, the length of the movement, gives the work that I needed to shift, to move the body. And I say movement, and if I say movement, it is a proper example for a rigid body, because the work may be also deformation of the body without moving it. But if you look at the single particles under deformation, they are moved. So if you, this definition, strictly speaking, applies to an elementary body. So the energy is measured, it's simply put, is the ability to do work then, and it is measured in joule, and it is, what is 1 joule? It is the work of moving an elementary body, moving at a distance of 1 meter, by applying a force of 1 Newton. So 1 Newton per 1 meter is 1 joule. Okay, so energy is essential to life, like water. It's indeed essential. And as I said, the sun is directly or indirectly, directly through solar radiation, indirectly through fossil fuels, for instance, is the source of all the energy available on Earth and used by people, animals, plants, and microorganisms. As I said, direct is radiation. Look at the last bullet point. And fossil fuels is an example of indirect energy from the sun. Because fossil fuels originated in the past, but they wouldn't build up, if they wouldn't form, if there was no organic matter in the past derived from ecosystems fed by solar energy. And remember, the Earth is a closed system, but for the energy that comes from the sun. Now, how much energy do we need? Much more than what we could expect. So let me give you through this slide some examples. If I want to produce 1 kilogram of meat, on average, I require 7 liters of oil. Keep in mind that oil may be like the joule, a unit for measuring energy, because if you burn 1 liter of oil, there is, you obtain energy which you can measure in joule. Of course, there is some energy lost in that, because when you burn, there is also some energy that is lost on heating the atmosphere. Like if you think of a car, the car is burning oil, and the energy is completely transformed. There is no loss of energy, but part of it is can be used to move the car, and part of it is used for heating the engine and then heating the atmosphere. And we will see that there is a difference between the two forms of energy that we can get, okay? And in both of the cases, even if you heat the atmosphere, you can get some work done. You can measure it in work, you can measure it in joule. But we will see that while if we produce a movement of a body, we can recover the energy, because we can use the moving body to produce electricity, for instance. When you heat a body, there is no way to get this energy back in other forms. So the global energy is conserved in the Earth system, but the part of it that we can use for, we can convert, we can use is conserved in a way that it can be recovered. The part that of energy that we use for eating something, then it's lost. So we may desalinate 1 cubic meter of water. 1,000 liters is 1 cubic meter with 3 liters of oil. Producing a ton of aluminium requires about 5 tons of oil. Producing a car, this is a bit interesting, requires about 3 tons of oil. That is about 1/4 of the energy consumed by a car in its lifetime. So it's not only using the car that requires energy, it's also producing the car. When we talk about greenhouse gases emission, it's it's also producing the cars that requires emissions. So, we need a lot of energy, and then the question is how we can produce it. So, now, how can we produce it? Today, it is very popular, the term energy transition, which means that we should progressively shift our energy production to a system that uses only renewable sources. What is the definition of a renewable source of energy? It's a source of energy that can be replenished after it has been used to produce energy, can be replenished, and replenished within a reasonable time scale. And with a reasonable time scale, I mean the time span, a time span that is comparable to the human life. So, for instance, if you think of hydropower, hydropower is water is a renewable form of energy. Solar panels are a renewable form. Fossil fuels, in principle, could be renewable because, they continuously build up, they continuously form up. But to form up, they require a length of time that is absolutely incompatible with our time scale, lifetime time scale. So we assume that they are not renewable. Actually, they are, but we assume that they are not, okay? And the same for biomass. Biomass is usually not considered a renewable source of energy. because it takes a long time to form up the biomass. So what is energy transition? Energy transition in general is a transformation of an energy system, which implies a structural change in both energy supply, but also in energy consumption. And it implies a broad shift in technologies for energy production. And today we use the term to indicate the transition towards sustainable energy production, renewable energy production. Actually, it's not only, I mean, we can call with the term energy transition any other transformation. And for instance, during the Industrial Revolution was supported by an energy transition because we made a transition towards a larger use of coal and coal-produced energy, and later natural gas produced. So I mean, an energy transition is something that is for sure possible, something that we for sure need, but on the other hand, it implies really a broad shift in our habit. And in particular, today, we are interested in trying to reach carbon neutrality. And be careful, the reason is not only climate change. I mean, when I was a teenager in 1980, climate change was not a concern, but we were already concerned by the possibility that the fossil fuels could be depleted. And there were a lot of concerns. So, I mean, avoiding the use of fossil fuels is indeed an imperative need for modern society. We need to get rid of it, absolutely, not only for climate change. So don't assume that it's only a climatic reason to transition. And this is what I repeat to some of my colleagues who say sometimes, look, we really don't need we don't need energy transition because we are not sure that climate change is originated by burning fossil fuels. And my reply is, yeah, but we are sure that fossil fuels will end, and possibly in the near future. So, I mean, energy transition is necessary. This is a way that I like to avoid controversy. I mean, in reducing the CO2 emissions, there are several positive effects, not only climate. So it's true that some of these reasons are affected by uncertainty, but some of them are not. So the fact that fossil fuels are going to run out, it's sure. So it's not really something that is optional. We need energy transition. But energy transition takes time, and unfortunately, in the public debate, sometimes there are interpretations that are too optimistic, and it is not a good thing. It is not a good thing to say that, like I heard in some political debates 5 years ago, by 2030 we will become carbon free. It's not a good thing, because when something is not realistic, we lose the trust of the public when people declare at any level, politicians, scientists, researchers, they declare something that is unrealistic. When we make predictions that turn out to be wrong, this is absolutely not a good thing, because the trust of the public in administration, in science now is quite low, and this is the reason why we can't succeed in mitigating climate change, because, I mean, it's the trust of the public. If it is low in the predictions that we make about climate change, of course, people don't give their vote in favor of climate policies. So we have to be careful of that. So I like this picture. It is not really, let's say, this is a resolution that is not very good. Let me get it at a higher resolution, because it's impossible to read, and even for me that I can see from the screen. I'm sorry, I am on the PowerPoint. So yeah, energy transition timeline. I think, let me see, I think here we have the high resolution picture. Let me check. Yeah, perfect. Now it's high resolution. So this figure starts from 2016, and let's start from here. 2014, coal peaked. So these are the different steps that we need to take, okay? And we start from the year 2016 with the 19% of the energy mix is non-fossil. We have to reach 100%, correct? So we start from the premise that an estimation that in 2014, the use of coal peaked. Actually, at least in Europe, with the onset of the war between Russia and Ukraine, there was some increase in the use of coal. But I think that indeed this estimation is reasonable. So the plan is, like when we move forward, why we move forward, oil peaks in 2023. I don't think we peaked in 2023, but again, this prediction didn't see the problems originated by the pandemics and the problems originated by the international geopolitical situation, which is, you know, it is quite delicate now. But we are very close to peaking with the use of oil. Peaks means that we start going down. Okay. Indeed, I read an article that is predicting for 2030 the peak now. 2026, we reach at the global level. These are estimated at the global level. The peak of the transport energy demand in 2024. This is the energy usage. Light electric vehicles reach cost parity with classical internal combustion engine vehicles. It means that in principle, 2024 is now, it was predicted that if you buy a small car, a car, let's say, for everyday use, in 2024, the cost, not only for buying it, but also the cost of maintenance, etc., should reach parity with the classical vehicles. I think we are not far from it. Still, we are not there. I wouldn't say that we are there, but we are not far from it. It depends on the kilometers, of course, because as you, of the usage, because as you know, filling her up, it's cheaper with an electric car, but the maintenance and the cost of buying it is still higher. But I think we are almost there. And then 2026, gas overtakes oil. I'm not really sure where we are now. I'm not an expert on energy, I should say this. Okay, you know what is my expertise, is water cycle, hydrology. I'm not very updated on energy situation, energy usage. What I do is to look at our world in data. But I don't think that in view of the recent evolution of the geopolitical situation, I don't think that the natural gas overtook oil. And in any case, I don't see the natural gas as a solution because it's going to deplete. Okay, 2023, you see seaborne container trade exceeds crude oil trade. This was a prediction. I don't think we are there, but okay, let's move forward. And let's see. Okay, perfect. I can use the arrows. Okay, so it is predicted here that in 2023, nuclear peaks. You know what has been my premise. I'm not really sure that we can reach a peak of the nuclear energy if we really want to get decarbonized. And then in 2034, natural gas peaks, 2039, manufacturing energy demands peaks. Okay, and let's go over the land. By 2028, 95% of world population has electricity access. I don't think it will become true. By 2031, wind overtakes hydro. I'm not sure it will become true. And I also think that why hydro is considered to be less clean than wind. It is less renewable hydro because dams have a limited lifetime. So it would be interesting if we could avoid hydropower production. It is absolutely not possible today, and I don't think wind will never be able to overtake hydro because hydro is prone to regulation. We can regulate hydro. We cannot regulate wind production. So I don't think this is a correct prediction. 2033, half of all light vehicle sales are electric, 2033. 2034, non-fossil caps overtakes fossil caps. And then 2035, world grid capacity doubles from 2016, which means grid capacity means the capacity of the electric grids, the electric network. And by 2038, wind supply gets 1 order of magnitude higher than 2016. Not sure. And here, by 2040, they plan to reach 10 terawatt of photovoltaic panels installed at the global level. And let me just move. And then you see the progress towards 2050. I'm not reading everything. The progress towards reaching carbon neutrality. Actually, what we can see here is by 2050, here there is the scale of percentage of energy mix non-fossils. What is predicted here is not really neutrality, but it is reaching the target of 50% of energy mix is non-fossil. And I'm not really sure here if natural gas is considered a fossil fuel or not. I would say yes. I would consider it a fossil fuel, and I'm not sure how they consider it here. And we could look at the Wikipedia page. So what is the moral of the story from this picture? The moral of the story is that the timeline is, it looks like a long time, but the timeline is indeed tight. It means that, you know, the steps that we need to achieve are several ones. And in my opinion, the big question here is the role of nuclear power. This is the big question. Keep in mind that, as you know, nuclear power may be derived through fission or through fusion. And currently we derive it through fission because it's the only way that we have so far to produce nuclear energy in large quantities, in large amounts. It is unlikely that we will get able to produce through fusion, nuclear energy through fusion by 2050. It's unlikely. I mean, we can already do that, but for very small quantities, it's unlikely that by 2050 we can reach a nuclear power production through fusion able to compensate a significant part of our demands. Fusion may be the future, indeed, because it's much less dangerous than fission. It's less risky. It presents less problem of displacement of the scores of the residuals. And it is definitely maybe an interesting option for the future, but it is unlikely that, as I said, it will be compatible with this timeline. In terms of nuclear power generation at the global level, you can find in our world in data some statistics which are interesting. So browse by topic, energy and environment, nuclear energy, here it is. There is a full page and article dedicated to nuclear energy, and this is the progress at the global level of nuclear energy generation. So you see that there has been a huge increase between 1970 and about 1995. Keep in mind that we had a disaster in the United States in 1971 and the Chernobyl disaster in 1986, which caused reaching this plateau. And then recently it started to increase again. But actually now the situation is that new nuclear powers, new nuclear reactors are only built when the older reactor go out of order. But indeed, recently, in the very recent years, there has been some initiatives taken in order to increase the nuclear power production. I think we can make a break here and let's meet again at 4:30. Do you have any question by chance? Okay, thank you. I apologize, I am a bit late. So let's go back to our presentation. 1 second. What was this? Okay. So let's try to learn more about energy then. And first of all, when we talk about energy, the first thing that is taught is that we have 6 forms of energy, and try to make clear in your mind this classification, because it is important, first of all, and also it's something that you may get into the quiz. You understand? It's something relatively simple and very basic. So these 6 forms of energy are thermal energy, chemical energy, electrical, electromagnetic energy, kinetic energy, and nuclear energy. And the chemical energy is the one that is stored by fossil fuels. And electrical energy can be considered a subsystem of electromagnetic energy, if you want. So here it is listed as a separate category, the electrical energy, because you understand the importance of it. But actually, it could be considered, as I said, a subsystem, a subdivision of electromagnetic energy. Now, it is possible to transform energy from one form to another form. And this table clarifies the possible transformations, and also there is the mention to the process through which you can make the conversion. So chemical energy can be transformed into thermal energy through combustion. And then chemical energy can be transformed to electrical energies through the processes that take place in batteries. So electrolysis. Chemical energy, electromagnetic energy is, for instance, the fireflies. And chemical energy into kinetic energy, mass holes. One thing, let me go back to the web page, because I don't remember one thing of this table, and it's written here. Okay, natural processes are indicated in red. This is what I want to say. 1 second. Natural processes are indicated in red. And so in any place you see the correspondence and the possible transformations. And other interesting, let's have a look at the red processes, electrolysis, then to transform electrical energy to chemical energy. And electromagnetic energy can be transformed into chemical energy through photosynthesis. Kinetic energy can be transformed into thermal energy through friction, and to chemical energy through radiolysis. And then kinetic energy can be transformed into electromagnetic energy through breaking radiation, and nuclear energy to chemical energy through ionization. In doing these transformations, you have a conversion from one form of energy to the other form of energy. And in particular, we can perform all the transformation processes that were listed in the table, that are listed here. A relevant question is whether, in doing this transformation, we lose something. This is a relevant question, of course. So, for instance, very often we need electric energy. So if we use chemical energy and through batteries we obtain electrical energy, do we lose something? Okay, first, let's look at the energy transformation law, the first principle of thermodynamics, which says that the total energy of an isolated system remains constant. Okay, so the energy can be converted, but in principle, we don't lose energy. Okay, and given that the energy is constant, we cannot talk of energy production. It's always energy conversion. Okay, so when we make hydropower and we produce hydropower, we sometimes say energy production through hydropower, electricity production. Electricity production is correct, energy production is not, formally speaking, because indeed what we do is to transform potential energy into electricity, electrical energy. And therefore we indeed generate electrical energy, but we can't say that we generate energy. So the total energy of isolated system remains constant. First principle of thermodynamics. Remember, the Earth system is an isolated system, but not from the point of view of energy. So let's just keep in mind this, and let's elaborate some reflection on this, okay? Perfect. However, the topic is not closed here, because you understand that during energy conversion, indeed, we lose something. So if we don't lose energy, what are we losing? We understand this, we know this. When we, for instance, when we burn oil into the car, we know that we are losing something. Or when we produce hydropower, we know that, for instance, the efficiency of the process is today very high. It is something like 4.75, which means that from 100 energy, 100 joule of energy, we get 75 joule of electricity. So it means that there is something, part of energy, that is not transformed into electricity. So where does it go? This is interesting to discuss. So conversion implies a degradation of energy. So the energy remains the same, but there is a part of it that we say it's degraded. What does it mean, degraded? That it cannot produce work anymore. So there is a part of energy that remains energy, but cannot be used to produce work. In fact, the second law of thermodynamics deals precisely with energy transformation and the natural tendency to move towards more degraded forms of energy, which cannot be used any longer. So I think it's not clear so far, the concept, okay? So what I said is energy is conserved, but part of it gets degraded, cannot be used to produce work anymore. Let me give you an example. The example is the car. The car, I burn the oil to move the car, but the engine gets heated up and the heat is transferred to the atmosphere. There is no way that I can use this heat to produce work anymore. So this is the energy that went to warm up the atmosphere. And there is no way that I can use this energy anymore to produce work. It is degraded. In general, the energy that is used to heat the surrounding of a body or to produce sound cannot be used anymore. If I collect this heat produced by the car, for instance, for producing power, steam power, then this would be a way to recollect part of it. But in any case, even if I use this heat to produce steam power, there would be some heat that is dispersed in the atmosphere. And this, as I said, cannot be used anymore. I cannot get the heat from the atmosphere to produce work. So you understand that indeed, in a closed system, you have some forms of energy that can produce work, and this is called effective energy, energy of good quality, and part of the energy that is cannot be used anymore. And therefore, this consideration should make you a little bit concerned, like, but then this energy that I cannot produce energy. So the part of the energy that gets degraded, I cannot use it anymore, means that I am moving towards a world where I will have less and less energy that I can use. This is for sure true. But there is a but. This is true for a closed system, an isolated system. So if you look at the universe is isolated. So the universe is indeed moving towards a form of energy, an increasing form of energy, which cannot be used to produce work. And the measure of this is entropy. In thermodynamics, you use entropy to measure the relative part of energy of the system that cannot be used anymore to produce work. And you know the statement, the entropy of the universe is moving towards a max. So for the universe, the constant is true. But for the Earth system, we cannot apply this concept as it is, because it's not an isolated system from the point of view of energy. So the Earth system is indeed getting more and more degraded energy, but on the other hand, we are getting replaced by the sun. And also there is another replacement that is done by the ecosystems. The ecosystems, which are not closed systems, can take, because the presence of living organisms can take some of the heat from the atmosphere and convert it into forms of energy that can be reused. So basically, it is applicable to the universe, but given that the Earth system is not closed, thanks to the energy from the sun is replacing part of the energy, and it's giving the fuel to ecosystems to get back part of the heat from the atmosphere. What is the difference between the universe and the Earth? The universe as a whole is indeed going to die, energetically speaking, because we know that the sun is going to deplete its energy. It's going to get turned off. So this is the difference, that when I consider the sun as part of the system, then the second law of thermodynamics applies. When the sun is not part of the system, it is like a battery. It's like a reserve of energy, which is for a certain amount of time continuing to supply energy to the Earth system. I think these considerations are extremely interesting. And of course, it would require more time in order to fully understand them, to make maybe an exercise and understanding, but it is indeed, in a way, giving you the basis to understand the system, the Earth system, the climate system. Now, one simple statement of the second law of thermodynamics, which I'm sure that you know, is that heat always moves from hotter objects to colder objects. It moves downhill in poor terms, with rough words, unless energy in some form is supplied to reverse the direction of the heat flow. Another definition is not all heat energy can be converted into work in a cyclic process. Okay, so I think we understood the difference between the good energy and the poor energy, the difference between energy speaking, strictly speaking, and degraded energy. Okay, and I think we also got that we can convert energy between forms, but there is always something that is lost. Okay, in terms of ability to produce work, In a way, from a very technical point of view, very roughly speaking, this is why we say we lose some energy. The process is not efficient. We lose some energy. Actually, we are not losing energy, but we are losing the ability to produce work. Very good. I think here there is nothing that I have to say. Fortunately, the Earth system and biological systems are open systems, as you can see here. Okay, fine. And therefore, thanks to the sun and thanks to the action of the ecosystems, we can, in a way, replenish our energy sources. Okay, and keep in mind, any form of energy, of the 6 forms that I mentioned, they are all coming from the sun. Even hydropower, if you think at hydropower, how the water goes up to the mountains through evaporation after solar energy. Okay, very good. Now, a second interesting classification of energy, primary energy and secondary energy. Okay, pay attention because this is terminology that is extremely important. Okay, primary energy consists of unconverted or original fuels, so petroleum, natural gas, coal, biomass, flowing water, wind, solar radiation. This is energy unconverted. Secondary energy includes resources that have been converted or stored. Okay, remember, this is a classical question in the quiz. What among these energies are primary energies? And it is a question that often the students don't get correct. So these are the examples, and there is a table of which I will show you. So secondary energy cannot be harnessed directly from nature. It's rather energy that, as I said, has been converted. For instance, electricity. Electricity, okay, it can be got from nature through lighting, but indeed we can't. You know that we can't get it. We can't get it really. So in practice, it's not available in nature. Electricity. It is something that we have to generate. So electricity is considered, with the exception of lightning, a secondary energy. Primary energy, but before we discuss about renewable or not renewable, let's look at the table that I mentioned to you. These are examples of primary and secondary energy. So primary energy, crude oil, hard coal, natural gas, liquids and natural gas in gas form, nuclear energy. This is primary energy, and also waste and wind, geothermal, biomass, hydroelectricity. Flowing water is a primary energy source. Here it's called hydroelectricity. It is a bit misleading because electricity actually it is not the same thing as flowing water. Hydroelectricity, it may be a synonym for flowing water, but please beware of the terminology. So flowing water is a primary energy. Electricity produced through hydropower generation is a secondary energy. Here, the term hydroelectricity is used to mean flowing water or water in general, okay? Potential energy and kinetic energy. Wave and tidal energy, primary energy. Secondary energy, petroleum products, like, for instance, the fuel for the car. It's a secondary energy because it's a petroleum product. It's not crude oil. And manufactured solid fuels and gases, etc. Electricity and heat are secondary energy. and biofuels are secondary energy because they are produced through cultivation of proper crops. Okay. Okay, now let me go back to the PowerPoint. 1 second. Can't find the mouse. Just one. Okay, here we are. Okay, now primary energy can be non-renewable or renewable. Okay, this classification applies to primary energy. Okay, and renewable energy is collected from renewable resources. We already mentioned this, and naturally replenished on a human time scale. And renewable energy includes sunlight, wind, rain, and tides, waves, and geothermal heat. Geothermal heat is considered to be a renewable energy source because it is something that it is assumed to be available forever. Actually, strictly speaking, it's not available forever, but it can be assumed for our time scale that is available forever. Okay, good. Now, renewable energy is, in a way, the opposite as fossil fuels. Fossil fuels are the typical example of a non-renewable energy. And because they are being used more quickly than they are replenished. And keep in mind that renewable energy doesn't mean sustainable energy. It's not an automatic association. There might be some forms of renewable energy that are not sustainable. And like, for instance, biomass sources are not considered to be sustainable at the current rate of exploitation. And also renewable energy, it doesn't mean that it doesn't have any impact. Actually, the impact is very significant. If you think of any form of renewable energy production, there is an impact on the environment, there is a socioeconomic impact. Think of dams for producing hydropower, think of solar farms, and think also of wind farms, which have an impact on the landscape and the noise. If you stand in the close vicinity of a wind farm, you understand that it's complicated to live there because the noise is really something disturbing. Okay, now primary energy. Some textbooks classify the primary energy into 3 parts. One is given by crude oil, hard coal, natural gases, nuclear energy. Another category is the waste for producing biomass, for instance, and the waste for producing gas, not biomass. And then there is a third category, including wind, geothermal, biomass, hydroelectricity, wave, and tidal energy. So how are these categories conceived? The third category here includes only energy forms that are renewable. Okay, biomass is not really clear if it is renewable. In some cases, yes, in some cases, no. But the third category includes the renewable sources. And the first category includes non-renewable sources. The second category is waste. It's placed in a separate category because in principle it could be considered a renewable source. On the other hand, it is hardly sustainable. It is really impacting the environment to a large extent, and recently in several countries there has been a limitation of the use of wastes for producing energy. There has been a limitation in terms of policies for limiting the use of landfills for displacing wastes. And there is a preference for the use of waste burners, which still have an impact. So in some countries are not readily accepted and still present sustainability problems. In a way, I mean, indeed wastes need a separate category, because it's something that, I mean, on the one hand they are renewable, but on the other hand they are not sustainable. So it's really something that deserves a separate treatment. Okay, and here you see that here I have written the note. Note that hydroelectricity is meant to indicate energy contained in flowing water. Therefore, it is primary. Primary energy is measured usually in tons of oil equivalent, TOE. Okay, good. Now, this is the table which I have already shown to you. And you see the process of transformation in order to pass from primary energy to secondary energy. Transformation can also be used to pass from different forms of secondary energy. Now, so what's the matter here? The matter is that the problem or the opportunity is that energy production is the driver of most of the global emissions of greenhouse gases. And in fact, let's look at our world in data. I think I still have here the web page. Let's see. Browse by topic, energy and environment, CO2 and greenhouse gas emissions. We already have seen this graph here. Emissions by sector. Let's see if I can get it. Okay, here it is. Energy production, 73% of the emissions. And this is an updated figure. It's an updated figure. It's 2020, updated to 2020. So it is the same figure that you can find on my website. And it is a basic figure for our course, our studies. So let's look again at the big picture, at the circle, at the inner circle. In the other circles, you can see the subdivision of each macro category in subcategories. Let's look at the inner circle. Energy is emitting 73.2% of the global emissions. Agriculture is around 18%, 20%, and industry is about 5%, and waste is about 3%, because waste treatment. Of course, energy includes transportation. But if you look at the details, what is interesting is that transport is responsible for about 16% of the emissions. So, and of this 16%, we have road transport that is accounting for about 12% of the emissions. And it means that even if we stop completely our cars, the benefit would be something like 10%. And it's still half of the emissions of agriculture. Aviation is, I think we already noticed that, 2% of the emissions. So, I mean, it really doesn't make a big change if we stop at all the planes. Of course, the message is clear. So I think planes reducing the flights is important for delivering a message. On the other hand, if we take the train, it's not that we zero our emission, because still the train needs electricity, and electricity is produced through energy, through emissions. Of course, depending on the type of travel that you make, depending on an overall assessment, which is a bit complex, it may help taking the train instead of taking a plane for a short travel. So if I need to go to Rome, for sure, it's better if I was assisted by a working policy that may limit the number of flights. If I need to go to Rome, it's much better if I take the train, because the railway is already existing, the transport system is already existing, and if you increase the number of trains and you decrease the flights, for sure you obtain a benefit. On the other hand, for international traveling, of course, it's a completely different story. And even if you have to make a long travel by train, it becomes questionable whether it is preferable to travel 24 hours by trains or 1 hour by plane. It is questionable, but still, I think that this figure is what should drive us in order to discuss what is the implication of getting to net zero. It is extremely important that we have in mind these percentages. Okay. And yeah, these are the figures that are reported in my website, because this graph was not updated recently after 2020. On the other hand, it is interesting to look at the other information that is reported here, because other information may be updated more recently. And I think it is also interesting to look at the emissions by countries. And if you browse our working data, you get also information on that. It is interesting indeed, because sometimes we don't have the perception of the dimension of the problem and the internal structure of the problem. So it is indeed a geopolitical problem, but sometimes we don't realize that it's a problem that is confined to few countries only, while other countries are, in terms of emission, best, well performed, meaning. Okay. This is the graph. And here is an interesting graph of the primary energy use and by fuel type. Okay, so this is divided in historical and projections, and by, as I said, by fuel type. So it's nuclear energy below, renewable energies, and it's the light blue line, natural gas, coal, and liquid fuels. Okay, so it's, of course, the liquids derive from fossil fuels, and therefore, basically, if you put together natural gas, coal, and liquids, you get the contribution of fossil fuels, which is still a relevant contribution for energy production. Remember, we are talking here of marketed energy, not electricity. For electricity, the picture is slightly different. Okay, here another interesting figure which dates back to 2018, World Energy Balance. And basically it is what I already reported based on the previous graph. Fossil fuels, coal plus oil plus gas, 81%. And it's the energy balance of the world. Nuclear is about 5%, hydro, and this is energy, again, not electricity, okay, energy. Hydro, 2.5%, biomass, 5%, wood, 5%, and then there is a small contribution of wind, and just to give you the picture 5 years ago, wind, 0.61% of the total energy balance. And geothermal, these are very small contributions. Wind turbines and solar panels make about 1% of world energy. This percentage is increased in the past 5 years, but not much. They didn't double. So here you read 0.8, I would say that we should be around 1.2%. So this is something interesting if you think that 5 years ago, when I showed this graph, I showed it because there were predictions by, it is always election period in the modern world, and it was an election period, and some statements were given by the media, like by 2030 we will get completely renewable, we will get net zero and completely renewable. And you see 81% of energy production based on fossil fuels, and this person was stating that in 12 years we would replace 81% of the total energy production. It was absolutely not credible. Now it's clear that it's not credible, but it is also important to take into account the variability of the renewable sources. Wind turbines and solar panels are characterized by a variable regime, and solar panels, it is a periodic regime, predictable. For wind, it's not predictable. But in any case, keep into account that energy cannot be stored. We can store limited quantities in batteries, or we can store part of it by moving water upstream. But it is really a limited storage. In the electricity network, it is not stored. This means that when I turned on these lights, when I came in, somewhere there was a turbine that increased its velocity when I turned it off. I turned on the light, and when I will turn off it, when I will shut the light off, there will be a turbine decreasing somewhere. I say turbine because when I talk about electricity in Italy, more than 20% of electricity is produced by hydropower in Italy. At the global level, we will see the numbers. Electricity covers more than 16%. It's around 17%. In Italy, it's more than that because we have a mountainous area, mountainous landscape, and then we have a lot of electricity production. Sorry. Okay, so half of global energy is produced by China, the United States, and the Arab state of the Persian Gulf. Of course, the Arab states for the fossil fuels, and also United States for the fossil fuels, and also in China they use a lot of coal. And when you say that half of global energy, it means that 80% of it, of this half, is fossil fuels. So the Gulf states and Russia export most of their production largely to the European Union and China, where not enough energy is produced to satisfy demand. This slide dates back to 2018, 2019, when I started delivering this course. And probably it was, maybe it was 2020, I think. The situation has changed a little bit, you know why. And you know the consequences of this change in terms of bills and in terms of cost of energy production. Energy production increases slowly, except for solar and wind energy, which grows more than 20% per year. But on the other hand, you understand that 20% of 0.8% is 0.96% after 1 year. So this is why I said in the past 6 years, maybe that we got to 1.2, 1.3. Renewable energy is emerging as a very good opportunity to decrease global emission, but in turn it entails a significant environmental impact. We already mentioned that. Okay. Let me move to the last slide for today. So, energy production before 2021. Energy is processed to make it suitable for consumption by end users, okay? And in particular, energy is converted in some of the cases. For the CBUs, we know that the most use that we make for energy is through electricity. Of course, we use also energy in forms of fossil fuels for feeding the car, but electricity plays a relevant role. And so it turns out that there are many conversions that are done in order to deliver the energy to the end users. And in particular, if we need to transport it, because electricity needs to be transported by electric lines, and if we want to make a transportation to a very long distance, we need to use different forms, and maybe that we need to use some conversions. So let's see, these conversions implies some losses in terms of production of degraded energy, as we discussed. And at the global level, unfortunately, about 25% of the energy is lost during these conversion processes. And it is, I mean, even if we are replenished by the sun, this is, in terms of costs, it is a percentage that is unfortunate. It's maybe to some extent unavoidable, but it implies an increased cost for the end users. Okay, so let's look at these percentages at the bottom of the slide to conclude. It's interesting to note that the global final energy used is given by the figures that you see here. The source is the International Energy Agency 2017. Residential, 21%, transport, 30%, industry, 30%, other, 21%. In order to get an idea of what is the final purpose of this more than 70% of global emissions. I think we can stop here for today. Do you have any question? Okay, thank you very much. And okay, let me stop the recording.